and share my screen. Where is my... Oh, nice. Yeah, I know that holiday is always nice. So, okay. Can you see the screen? Okay, so let us start. So, okay. Right, so I have pen ready. So, well, last time we finished our Boolean expression. So make sure you finish the, see, if you finish the data structure with the stack, you know how to analyze the arithmetic expressions. Also, you know how to evaluate your Boolean expression. Actually, they are treated as the same. And also the thing is your stack is associated with the memory. So stack, you cannot create a new thing for the stack. Actually, the stack is also within the memory. So it's also in the data memory, so in the RAM. And you can also do the same thing for the Boolean expression. So evaluate the Boolean expression and get a true or false. Of course, in our, make sure in our hack machine, we don't have true or false in our hack machine implementation. Actually, we will generate the value 0 or -1. If it's a Boolean expression, it's true, it will be -1, otherwise it will be 0. So if you have problem with this value, you can look back to our assembly and assembler slice. So they will give you the value at that time. It's not true or false. Because if you handle true or false different from the number, you say that this is different from the number, actually you need two systems. Okay, you write not the number, but also you will write the string like true or false, or you write the character F or T. This one will give us a headache for the implementation. So actually here, if it's false, it will be 0. In our hack machine, if it's true, it will be -1. If you do or, you add them up, it will be -1, right? If you add, it will be -1. If you do and, you will multiply. False will be 0 and true will be -1. You multiply, it will be 0, right? So this one is the same thing you do arithmetic. So that's why we say that our Boolean expression, actually we can treat like the same as the arithmetic. You can do the same thing as arithmetic. Okay, so for our hack machine, we support 3 arithmetic thing and another 5. Yeah, another 5 for logical operations. So oh, this one for the logical expression, you can also treat like three. So 2 parts. This one is compare with numbers. This one is actually do bitwise Boolean expression. Okay, so this is still deal with the number, but it will give you the output will be true or false, or will be 0, -1. This one is definitely do the arithmetic. You do add, sub, negation. So it's definitely arithmetic. This one is compare. The output will be the Boolean value. And this one, the last 3, this one is bitwise Boolean expression. Okay, so this we partition into 3 parts. And now we need to implement our stack in the memory. The thing is that our memory, when we deal with the high-level language, we will have 4 parts we need to think about. The first part is the class level variables. So the variable like static variables. You have the private variables, for example, your fields. In Java, we call it fields. So we declare in the class level. We have object-oriented programming. We have the class level variables. We also have the method level. So method level associated with each method, you will have local variable. Within the method, you can declare certain kind of variables. This one we call the method variable. Also, we have the argument variables. So the argument is passing value to the method. So we first need to implement in our virtual machine and in our data segment. So in our data RAM, we should have some virtual memory segment. So virtual memory segments, and this one, the first one is the static. So static one, it will be in the static, and private variable will record at this. So private variable is the this segment. And then method level, we have the local variable, we record at the local in the virtual machine model, and the argument variable record at the argument. So as well as we do another thing is that a constant pointer and a temp. This one we will use it later, but it will be quite useful. So that is usually if you have method called another method, so you will use that to represent the other method. Okay, we will have a constant values stored in the virtual memory. So we have the pointer. So the pointer is quite useful because it will determine the when you return or you call other method, you will use the pointer to that. But the most important usage for pointer is when you return from one method back to another method, then you have to maintain the pointer to let the system know where is the place you want to return. So this is the pointer. We will discuss in next week when we deal with the method or function calling. Okay, we also have some temporary storage. You want to store some values. So this is temporary. Okay, so if we have the memory assessment command, we have the format for pop from the segment. So what kind of segment? This 8 segment. This 8 segment. So in our virtual machine, we will pop from certain segment and push to certain segment from the stack. Okay, these commands are used instead of pop X or push Y because the system, the virtual machine don't know where is X, where is Y. Remember that our virtual machine is on top of assembler. So assembler is below. So where we do this variable memory assignment is at the assembler, right? So assembler is lower. Assembler is lower than virtual machine. So at the virtual machine level, it doesn't know where is X, where is Y. So if you do pop X or push Y, it gets the problem for the virtual machine to understand or to generate assembly code. So what we will do is assembler will assign for the certain variable, then virtual machine will say, okay, what is variable belongs to which segment, whether it's the local variable or it is the static variable or it's the field, right? Field variable. So this one is actually what we do here. So the meaning of different 8 segments will become important when we talk about the compiler. Okay, the compiler will do this. So remember that we have 8 virtual memory segments. It doesn't need to know how big the size it is, but when you do the compiler, it will give you the size of that memory segment. It's based on your hardware. And but at the virtual machine level, there's no need to differentiate among the different rows of those segments. Okay, so this one is just at the virtual machine, it's just a need to know I need some space to store the variable, but the compiler will separate those 8 virtual memory segments, give the segment a different meaning. Okay. So I will erase. So as far as virtual machine programming commands go, a segment is a segment is a segment to access a particular segment entry. So the virtual machine program is just a segment and a segment and a segment. Okay, so it doesn't worry too much about which segment, what's the meaning of each segment. Okay, this is what they say. Okay, now we look at the compiler, what is the look like. Here is the example. So we want to multiply x with y. So we have this function. We have the result at the beginning equal to 0. And we have j equals to y. J is the local variable. Okay, so this 2 is the local variable. I write short, so local variable. And the result is the local variable, j is the local variable. And then I want the j equals to y. Y is the argument, right? This is the argument passing. The argument passing. Okay, so while j not equal to 0, results equal to results plus x, this is arithmetic expression. J equals to j minus 1 is the arithmetic expression. J equals to 0, this is the Boolean equation. And since this is a while, so you should create a loop. And finally, the return result, actually, you will push into your stack so that it will go back to the previous. Okay, so now we look at our compiler will do the virtual machine code first approximation. So I have the function name. You don't need to worry too much about the function name. Later, when our next 3 classes, we will talking about the function control. So here you just treat like this is a name, okay? You can eliminate this guy. And I will first push 0. This is the constant, right? 0 is the constant. So this is the constant. Yeah, so the constant here, 0, constant. And the pop result means I want to put 0 into the result, right? Push 0 into the result. Actually, these 2 things means result equal to 0. And the push y, so push y and the pop j, this 2 means j equal to y. Here I still use a variable, not use a segment. Okay, still use variable. Okay, now I start my loop, right? I will push j. So this is j, right? I want j and push 0. I will compare if it's equal, if then go to end. So this label end. Okay, so the next class we will do this if go to end, this kind of control. So stuff. And we will push result and push x, add x to the result and pop into the result. So this things means I do this, right? I do result equal to result plus x, right? So this result plus x and pop into the result portion. And the remaining, this one is this guy, right? J equals to j minus 1. Sub means j minus 1 and put into the j. And then I go back to loop, right? Go back to here. So it looks like a while loop. So this one is the control. So j, whether it's equal to 0 or not, right? So this one is quite straightforward. And then I push the result into the stack so that it will return. So next class, we will do function call and return. So in this class, you don't need to worry. And now this is the first generation of the virtual machine code. Just convert my local variable, my constant argument variables, and give the variable, still use the same variable name, but use push and pop to evaluate my function. Okay, so this is first, and then we need to represent this 0 as a constant 0, give the segment name. Okay, this is the result, so I don't need to write a result anymore because this time virtual machine generate the code just indicate which segment it will be. Okay, so the segment, since the result is the local, so it's the local segment, the first local segment. So the first portion at the local segment, so it's a position at 0. So then I have the argument y is actually, I have 2 arguments passing in the multiplication. So here it say that 2 arguments, right? 2 arguments into the multiplication. So y is the second, x is the first. X is 0, argument 0, and y is argument 1. So the first, actually this means the second argument. So argument 0, and then j is local. Since the result is already take the first position at the local segment, so j will be the second position. So you get local 1. Then I create a loop, then you just replace. So how do I do that is actually I will do, the compiler will do is x. They look at this code, generate this guy, and then it's create a table to say, okay, x is the argument 1. So this is the argument 1. I look at the code. So x will be argument, the first argument. So it will be argument 0, and y, I see x and y. So this is 2 passing. So I will do is argument 0, then argument 1, right, for y. Then I move forward to look at, so you push 0. So this 0 is the constant. So I will put is the constant 0. This is the first segment. It doesn't mean 0 here, okay? So this means the first memory in the constant portion, I will put 0 there. Okay, then I move forward to look at my virtual machine code first approximation, and I find the result. So I will put the result. I will put the result. I will put the result here to say, oh, this is the result. Result is local, right? So I will put a local. So this is local, is 0, right? This is the first local variable. So I will do 0. And then y is argument 1. So this is already in my table. So I will replace it as argument 1. J is not in my table. So I will create my table and hold it to say that j is still the local one. It's not argument. It's the local one, and it will be 1. Okay, local 1. So then skip the label loop. So I will do push j. J is a local 1, so I can replace, and the push 0 is the constant value. So it's a constant 0. So it's already there. So constant 0. So equal, I don't care. So then I go to the result. It's local 0. X. Okay, x is argument 0, right? It's already here. So result is local 0, j is local 1, then 1. So this is a constant, right? So I will put into the constant 1. So it's a constant. And then move forward, J is a local 1. J is a local 1, and then result is a local 0. Okay, so when I finish this representation with this table, I have mapping this table, right? I have already mapped this table. I have this table, then I can create my second approximation. This is actually the virtual machine code. Okay, so far so good. Any question? Okay. So now with this argument, I can move forward. I will do this, so erase. Okay, we can do this calculation. If we want to 7 times 3, then I have the local variable for 0 and 0. So J is 0, result is 0. So it's not summation. Actually, this one should be the result, right? So this one is the result. Okay, so the result. Okay, so the result is 0 here. And then I will do the stack evaluation because everything is push pop, right? Eliminate the loop, okay? Eliminate the loop label, something like that. If I just do the push and the pop, it's mostly, it looks like to do the push pop on the stack. Okay, so this one is the virtual machine code. Now we should move forward for the virtual machine code and move to how do we do this push and pop, right? We can do this arithmetic evaluation, use the push and pop. We can memory access, use push and pop. Then the question is, how do I implement this segment into my virtual machine or into my hack platform? How do I create? So in our assembler, we have already said that we have some reserved variables or space for some values, right? So we have implementation, we have multiple possible ways. The first one is software-based. Probably the most famous one is the Java virtual machine, is software-based. So it's associated with Java. So this one is software-based. Software-based is a headache to see inside. So as an example, we will do the translator-based is our machine, so hack machine. And of course, you can do the hardware-based virtual machine. So this one will realize the virtual machine using dedicated memory and the registers, not share with the ROM and the RAM in the computer, but you will set up another place only for the virtual machine. So well-known translator-based, and this one, the software-based, usually will based on the translator. So the famous one is the Java virtual machine. Although it's a software-based, actually it's translate the code one by one. So this one is still the translator-based. So most of VM famous one is the translator-based virtual machine. So now, let us show an example for our hack machine. So still remember, we have 0 to 15 is reserved, right? We say this portion is reserved. Now, they have some meaning. Okay, so the RAM 0, the RAM 0 is for stack pointer. So stack pointer. And the local variable, the first one, the first RAM with address 1 is for the local variable. So this one is local, and the second one for argument, and the third one for this, fourth one for that. Actually, this one is the pointer. No, here to here. So sorry. Should write erase. So from here to here is store is the base address. So we will see why it means base address. This base address is the first local variable or first argument variable, first segment, first portion of the local or first portion of the argument. So this one is solved address as here. And then if you have more local variables, then you will store at the heap, okay? Store at a heap or stack. So stack is for evaluation, so you will store at a heap. Okay, from 5 to 12 is a temporary variable segment, temporary segment. You may store your constant or whatever. So you can also store in the general purpose from 13 to 15. And then static variable will store from 16 to 255. So for the static variables, shared by all the programs. So this one will be the static variables. And we do the stack evaluation. So the stack will be starting from 256 to 2047. So it's for the stack. The remaining for the heap. So we store it as a heap. So now let us to see is how we map the segment. How do we map the segment into the host RAM? So, and then given this map, how we implement our VM command using assembly commands that operate on the RAM, okay? So this is two challenging things. We will do the first, and then I will give you some exercise in the class for the second challenge. So how do we map, okay? So first, for the local argument, this Z mapped on the heap. So this things will map to here, the heap. And how do we organize that is we have the base address actually is the first variable, the address for the first variable. So this is the base. And then if you want to access, for example, the second entry, then you need to use the base address plus 2. You can treat it like an array, right? So here I store an array 0. So array 0, so ARR 0. This is the base address, right? So how do I access array 0 is the address put at here. How do I access the array 1? I need to use the base address plus 1, right? The base address, this is array 0, right? Array 1 will be the base address plus 1. Then you get the second local variables here. So same as the argument, this is that. So this is the same implementation. So the static is quite easy. You just put that here. So you just put a variable, static variables here. So it's starting from 16, right? So in our assembler, they will give you the available memory address. So if it's a static, it will be here. Then constant is another thing, is truly a virtual segment. If you want to access the constant I, then is implement by supplying the constant I. So this one is just put at a temporary, or you can directly access it. So you don't need memory, right? So then the pointer use this and Z, this two, this and Z, it will see that which blocks it will be there. So use this one, you can access pointer. So this one is actually will be useful when we do the machine, when we do the function return. So this one we will discuss at the next class. So this is the implementation. So the map virtual machine segment to the host RAM. Now, I give you some exercise to do for the command and write a symbolic code, so assembly code for this one. So I give you 10 minutes for push argument 5. So here is the segment. So push argument 5. Okay, let us see the results. So here is assembly. We do the push argument 5. So we want the first thing is if you push the items into the stack, so the stack will get the value and increase its value. Okay, so now let us see what happens. So the first one is I try to make sure where is the argument. So where is this value? So first I will add argument and d equals to m. So d equals to m, I get the base address. So this one is the base address. Right, so I need to add 5, right? So to access argument 5, so add 5 and a equals to d plus a. So now this one is the argument 5 address for argument 5. So I get address for argument 5. So then I can get the value, right? So now I can use d equals to m. So get the value. So from this one, actually, I get the value and put into the D register. And now I try to push into the stack. So where is my stack? So at SP is the stack. So give me the stack address. So A equals to M. So this is the address of the SP, right? The address SP points to. So I got the address SP points to. So this is my stack header. So stack. So this one is the address. And now I want to put this value because I get the value and store in D. So I put this value into the memory. So actually this means I push the value, push argument 5. So push the value to the stack. But make sure I need to, at SP, I need to make it increase by 1, right? So the SP always point to the first available slot in the stack. So this is the whole thing I need to do. Okay, so move SP to the next available slot, right? So this is the whole thing. Okay, everyone got the idea? Okay, now, so this is one sentence at virtual machine is convert to that longer assembler, so assembly language. So, but it's doable. So everything, if you do the push, the only things you need to change is this guy, you change 5 to, if you argument 2, then you just put 2 at here. So changes automatically. So you can do is, okay, I can put everything. This is the structure, the code. If I find this push, then I just replace by this, okay. Okay, so now that's all for today's class, and I have another one for you to practice. Is a pop local too, so you can practice at home. So I don't have time to go over the whole thing for pop. Okay, for the push I have already done, so you can use the same style for pop and try at home. So any question? Okay, if you don't have any question, we stop at here and see you next Monday. Okay, have a nice weekend. Oh, bye.